Welcome to For Science Salah Lotfy channel. Today we dive into a remarkable breakthrough in polymer science, one that harnesses the power of radiation to create advanced materials with exceptional properties. Scientists have successfully developed a new polymer composite using N-vinyl 2 pyrrolidone and acrylic acid. What makes this material extraordinary is the way it reacts to radiation exposure. When subjected to controlled radiation doses, its molecular structure undergoes a process called cross-linking, which significantly enhances its durability, thermal resistance, and chemical stability. To study its properties, researchers used differential scanning calorimetry, also known as DSC. The results were fascinating. As the radiation dose increased, the polymer's melting and transition temperatures changed, indicating a stronger molecular network. This means it can withstand higher temperatures, making it ideal for applications where heat resistance is crucial. But that's not all. This polymer exhibits a unique property. It can selectively absorb certain ink components while blocking others. This opens the door for potential applications in water purification, ink removal from industrial waste, and even smart filtration systems. Imagine a material that can efficiently separate contaminants from water without relying on harmful chemicals. Now let's talk about the broader impact of this discovery. The benefits of this innovation extend beyond the lab and into real-world industries. Reducing industrial costs, radiation-based polymer processing minimizes the need for expensive chemical additives, making manufacturing more cost-effective. Environmental sustainability. The process eliminates toxic solvents, supporting global efforts to develop eco-friendly materials, revolutionizing water treatment. With its selective filtration properties, this polymer could be a game-changer in addressing water contamination issues, strengthening local and global industries. From packaging to pharmaceuticals, this advancement has the potential to boost polymer-based industries, particularly in Egypt, where innovation in material science is crucial for economic growth. Scientific advancements like this demonstrate how research can directly impact industries, economies, and even our daily lives. With continued development, smart polymers could become a key technology in tackling environmental and industrial challenges worldwide. If you're passionate about the latest in science and technology, subscribe to For Science Salah Lotfy channel. Stay tuned for more exciting discoveries. Welcome to For Science Salah Lotfy channel. Today we highlight a remarkable breakthrough in polymer chemistry, an innovative approach to industrial ink waste treatment using radiation technology. A team of distinguished researchers including Dr. Mai Mostafa Mohamed from the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt, Professor Dr. Saber Ibrahim from the Packaging Materials Department, National Research Center, Doki, Giza, Egypt, and the Nanomaterials Investigation Laboratory, Central Laboratory Network, National Research Center, Doki, Giza, Egypt, and Professor Dr. Salah Lotfy from the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt, have developed poly-N-vinyl 2 pyrrolidone acrylic acid superabsorbent hydrogels. Their research, published online by Gruyter in March 2025, explores the impact of gamma irradiation on these advanced materials. So, why is this research important? These hydrogels have been engineered to possess exceptional water absorption capacity and selective ink removal properties, making them an effective solution for treating industrial wastewater. By exposing these polymers to controlled gamma irradiation, researchers have significantly enhanced their stability, swelling properties, and efficiency in separating ink particles from water. The scientific and industrial significance of this research is profound. 1. Revolutionizing industrial wastewater treatment. These hydrogels can efficiently remove ink waste, making industrial processes more environmentally friendly. 2. Promoting sustainable technologies. Unlike traditional chemical-based treatments, radiation-modified hydrogels eliminate the need for toxic solvents, supporting global environmental sustainability goals. 3. Enhancing cost-effectiveness. The use of gamma irradiation simplifies the polymer modification process, making large-scale production viable for various industries. This groundbreaking study not only advances material science, but also strengthens Egypt's role in global scientific innovation. With further research, such smart hydrogels could be applied across multiple fields, including wastewater management, sustainable packaging, and biomedical applications. Scientific discoveries shape the future. Stay connected with For Science Salah Lotfy channel for more insights into cutting-edge research.
Hey there, science enthusiasts! Welcome back to my channel. Today I've got something super cool to share with you how advanced hydrogels are revolutionizing ink waste management. Alright, let's dive in. Imagine a world where we can efficiently clean up all that messy ink waste from printing. Sounds like sci-fi, right? Well, it's not. It's happening now, thanks to some groundbreaking research. So, what's the magic ingredient here? It's called a superabsorbent hydrogel. Researchers have cooked up this fantastic material using something called gamma irradiation. Fancy, huh? But here's the kicker. These hydrogels can soak up massive amounts of water, separating ink from wastewater like a pro. Let's break it down. This study was led by Dr. Mai Mostafa, Professor Dr. Saber Ibrahim, and Professor Dr. Salah Lotfy from Egypt. They created a hydrogel composed of poly-N, vinyl, 2-pyrrolidone, and polyacrylic acid, or PNVPAAC for short. Now, using gamma irradiation, they synthesized these hydrogels and tested them at different doses. At 10 kgY, they struck gold. The hydrogel had a gelation percentage of 99% and a swelling capacity of 12,000% at pH 11. And get this, it swelled up to 48,000% at 60 degrees Celsius. That's some serious absorbing power. But how does it work in the real world? When they tested it on industrial ink solutions, these hydrogels achieved an impressive 87.5% separation rate. That means they could recover water through a process called forward osmosis. This is huge for industries. Imagine reducing waste while reusing purified water. The hydrogels also showed excellent water retention, with only 75% of absorbed water evaporating over 50 hours. Talk about efficiency. To ensure these hydrogels were up to the task, the team conducted some high-tech analysis. Density functional theory, DFT, revealed a high pore volume of 84 cc per G and a surface area of 136 square meters per G. Differential scanning calorimeter, DSC analysis showed they had enhanced thermal stability. Fourier transform infrared spectroscopy, FTIR, and scanning electron microscopy, SEM, confirmed a highly porous structure, perfect for absorbing water over ink. So why should we care about this research? First off, it's eco-friendly. These hydrogels offer a cleaner way to handle ink waste without harmful chemicals. Secondly, they help conserve water by recovering it from industrial waste. And finally, the production process is scalable, making it cost-effective for industries. Egypt is leading the charge in this scientific breakthrough, showing how radiation technology can solve pressing environmental challenges. In conclusion, these superabsorbent PNVPAAC hydrogels are a game-changer for industrial wastewater treatment. With further research, we could see them used in agriculture, medical applications, and more. Thanks for watching. If you found this video interesting, don't forget to like, subscribe, and hit that notification bell. Stay curious and let's keep exploring the world of science together.
Hey there, science fans. Have you ever wondered how a baby diaper keeps things dry? The secret lies in a fascinating material called superabsorbent hydrogels. These incredible polymers can soak up to hundreds of times their weight in water. Imagine a sponge that can hold a bathtub full of liquid. That's the power of hydrogels. They're like tiny molecular sponges with an unquenchable thirst for water. But their talents don't stop there. These hydrogels aren't just good at absorbing water, they can also release it when needed. This makes them incredibly versatile for a wide range of applications. From agriculture to healthcare, these amazing materials are making a big splash. Hydrogels are revolutionizing how we manage resources and tackle environmental challenges. And today, we're going to dive into one of their most exciting applications, cleaning up printing ink waste. Get ready to explore the science behind these superabsorbent wonders. Let's go. Now, not all hydrogels are created equal. Just like we have different tools for different jobs, scientists have developed a variety of hydrogels tailored for specific tasks. Think of it like this. Some hydrogels are like all-purpose cleaners, while others are specialized for removing tough stains. Researchers have become really good at tweaking the properties of hydrogels. By adjusting their chemical structure, they can design hydrogels that target specific pollutants. It's like giving them a nose for sniffing out and capturing certain molecules. This is particularly important when it comes to cleaning up complex mixtures of pollutants, where we want to remove the bad stuff while leaving the good stuff behind. Some hydrogels are designed to attract heavy metals, making them ideal for cleaning up industrial wastewater. Others are engineered to break down harmful organic pollutants like pesticides. By carefully selecting the right hydrogel for the job, we can develop more efficient and sustainable solutions for environmental remediation. It's all about working smarter, not harder. Let's talk about printing ink. It's everywhere. From the packaging of our favorite snacks to the magazines we read, printing ink adds color and information to our world. But behind those vibrant hues lies a messy truth: printing ink waste. The process of printing and packaging generates a surprising amount of waste ink. This ink often ends up in landfills or is incinerated, releasing harmful pollutants into the air we breathe and the water we drink. Not cool. The challenge with printing ink waste lies in its complex composition. It's a mixture of pigments, solvents, and resins that can be difficult to break down and remove using traditional methods. But don't worry. Science to the rescue. That's where our superabsorbent heroes, the hydrogels, come into play. Section 4. Gamma-irradiated hydrogels, a shining solution for ink waste. Remember how I mentioned that scientists can tweak hydrogels for specific tasks? Well, they've done just that for tackling printing ink waste. By exposing certain hydrogels to gamma radiation, scientists can enhance their ability to absorb and retain ink molecules. It's like giving them a super boost of cleaning power. These gamma-irradiated hydrogels work by creating a network of tiny pores that act like a trap for ink molecules. Think of it like a microscopic net that captures and holds onto the ink, preventing it from spreading and causing further contamination. And the best part? These hydrogels can be used multiple times. Once the hydrogel is saturated with ink, it can be easily removed and treated, allowing for the recovery and reuse of both the ink and the hydrogel. Talk about a win-win situation. This closed-loop approach to waste management not only reduces pollution but also conserves valuable resources. Now that's what I call smart science. Section 5. Poly-N, Vinyl 2-Pyrrolidone Acrylic Acid, Hydrogels, the science behind the absorption. Okay, science fans, let's get a little more technical for a moment. One type of hydrogel that has shown great promise for removing printing ink is called Poly-N, Vinyl 2-Pyrrolidone Acrylic Acid, or PVPAA for short. PVPAA hydrogels are particularly effective at absorbing ink because of their unique chemical structure. They contain both hydrophilic or water-loving and hydrophobic or water-repelling components. This duality allows them to interact with and capture both the water-based and oil-based components found in printing inks. The hydrophilic parts of the hydrogel attract and trap the water molecules in the ink, while the hydrophobic parts latch onto the pigments and resins. It's like having a team of specialized cleaners working together to remove every last trace of ink. This makes PVPAA hydrogels a highly efficient and versatile solution for cleaning up printing ink waste. Section 6. A cleaner, greener future. The impact of smart hydrogels. As we've seen, smart hydrogels like PVPAA have the potential to revolutionize how we manage printing ink waste. By providing a sustainable and efficient method for capturing and removing ink, these amazing materials are paving the way for a cleaner and greener future. But the impact of smart hydrogels extends far beyond the printing industry. Their ability to target specific pollutants makes them invaluable tools for addressing a wide range of environmental challenges. From cleaning up oil spills to removing heavy metals from contaminated water, hydrogels are helping us create a more sustainable future. So the next time you see a baby diaper, remember the incredible science happening inside. Those tiny hydrogels are not only keeping things dry, they're also inspiring a new generation of eco-friendly technologies that are making our planet a cleaner and healthier place to live. Keep asking questions, keep exploring, and keep on innovating. Welcome to For Science Salah Lotfy channel. Today, I'm diving into a groundbreaking study on revolutionary hydrogels that could change the way we manage ink waste. Let's get started. In this study, researchers used N-vinyl 2-Pyrrolidone and acrylic acid to create a copolymer hydrogel. These materials were mixed in a 70-30 ratio to balance hydrophilic and hydrophobic properties. The result? A hydrogel perfect for absorbing and swelling with water, with potential uses in medical devices, drug delivery, and coatings. The synthesis process? A bit more complex. Scientists mixed NVP and AAC, then exposed them to gamma irradiation at 0.8 kGy per hour using a cobalt-60 cell facility in Cairo. This kicked off polymerization and cross-linking, creating stable hydrogels. After a thorough wash and dry, the final copolymer was ready for analysis. Next, they conducted gelation and swelling measurements. By drying the hydrogel before and after immersing it in hot water at 60 degrees Celsius for 24 hours, they determined gelation. Swelling tests showed how the hydrogel responded to different conditions like irradiation dose, pH levels, and temperature. Water retention was another key factor. By allowing hydrogels to swell to equilibrium, then weighing them over time, researchers assessed how well the hydrogel retained water. Now, onto ink waste treatment. The hydrogel was tested for its ability to extract water from ink waste using a batch technique. By adjusting pH, irradiation dose, and temperature, researchers optimized the process. The efficiency was measured by the amount of water absorbed. To fully understand the copolymer, advanced analytical techniques were used. FTIR identified functional groups. SEM provided surface and cross-section morphology insights. DSC analyzed thermal behavior, and nitrogen adsorption measurements determined the surface area. Freeze-drying ensured accurate sample preparation. In summary, gamma-irradiated copolymer hydrogels hold great promise for various applications. Their water absorption, retention, and ink waste treatment capabilities make them invaluable. Future research could optimize these properties even further. Thanks for watching. If you found this research fascinating, like, share, and subscribe to For Science Salah Lotfy channel for more groundbreaking discoveries. Hi, science fans! Today, we're talking about gamma radiation. It sounds scary, but it can be used for good. Gamma rays are like super-powered light, and we can use them to make amazing materials called superabsorbent hydrogels. These hydrogels are like sponges, but way better. They can soak up huge amounts of water, even hundreds of times their weight. So how does it work? We start with tiny molecules called monomers. Think of them like little Lego bricks. Gamma radiation acts like a special tool that connects these bricks together. This creates long chains called polymers, which are like long Lego structures. These polymers then link together to form a network, kind of like a web. This web is what makes the hydrogel superabsorbent. When the hydrogel comes into contact with water, the water molecules get trapped inside the web, causing the hydrogel to swell up like a balloon. This technology has the potential to revolutionize many fields. Imagine using these super hydrogels to clean up polluted water, help crops grow in dry areas, or even deliver medicine inside the human body. Pretty cool, right? Now let's dive a little deeper into how gamma radiation turns those little monomers into giant polymer networks. It's a three-step process: initiation, propagation, and termination. First up is initiation. The gamma rays hit the monomers, giving them a burst of energy. This energy makes the monomers reactive, kind of like making them want to hold hands with each other. Next is propagation. Remember those hand-holding monomers? Well, they start linking together, forming longer and longer chains. It's like a chain reaction, with each new monomer joining the growing polymer chain. Finally, we have termination. This is where the chain reaction stops. It can happen in a couple of ways, either by two growing chains joining together or by a special molecule stopping the growth of a chain. And voila, we have a network of polymers that can hold tons of water. It's like magic, but it's science. Now let's talk about radiation dose. It's like baking a cake. You need the right amount of heat to get it just right. Too little, and the cake will be gooey. Too much, and it'll be burnt. The same goes for making hydrogels with gamma radiation. The dose of radiation is like the amount of cooking the monomers get. A low dose might not be enough to link all the monomers together, resulting in a weak and gooey gel. On the other hand, a very high dose can break down the polymer chains, making the hydrogel brittle. Finding that just right dose is crucial. It's like finding the sweet spot where the hydrogel is strong, elastic, and can hold the maximum amount of water. Scientists are hard at work figuring out the optimal dose for different types of hydrogels and their applications. Section 4, hot or cold, acid or base, how temperature and pH affect swelling. We've made our superabsorbent hydrogel, but the fun doesn't stop there. The way these hydrogels swell up can be affected by temperature and pH. Think of it like this: a sponge might soak up more water if it's warm or if the water is a little acidic. Temperature affects how fast the molecules move around. A higher temperature usually means the hydrogel will swell faster, but there's a limit. Too hot, and the hydrogel might start to break down. pH, which tells us how acidic or basic something is, can also play a big role. Some hydrogels swell more in acidic conditions, while others prefer basic conditions. It all depends on the type of monomers used to make the hydrogel. Understanding how temperature and pH affect swelling is super important for using hydrogels in the real world. Section 5, Super Hydrogels in Action, from cleaning water to healing wounds. So, we've learned how to make these awesome superabsorbent hydrogels and how their properties can be tweaked. Now let's talk about how we can use them. The possibilities are endless. One exciting application is in wastewater treatment. These hydrogels can be designed to absorb pollutants like heavy metals and dyes, cleaning up contaminated water and making it safe again. In agriculture, superabsorbent hydrogels can be mixed into the soil to help retain moisture. This is especially helpful in arid regions, allowing farmers to grow crops with less water. And in the medical field, hydrogels are being used for wound dressings, drug delivery systems, and even artificial tissue engineering. Their biocompatibility and ability to hold large amounts of fluids make them ideal for these applications. That's it for today. We've learned about the amazing world of superabsorbent hydrogels and how gamma radiation is used to create them. From cleaning our water to healing our bodies, these superpowered materials have the potential to make a real difference in the world. Keep on exploring and never stop questioning the world around you. The printing industry is essential to our modern world. It allows us to communicate and share information. However, this industry also produces a significant amount of waste. This waste, primarily in the form of ink, poses a threat to our environment. Traditional methods of ink waste disposal, such as landfills and incineration, are unsustainable. They lead to soil and air pollution. Fortunately, there is a promising solution on the horizon: hydrogel technology. Hydrogels are innovative materials with a remarkable ability to absorb and retain water. They can be engineered to target and capture specific pollutants, making them ideal for ink waste management. These materials act like tiny sponges, soaking up excess ink and preventing it from contaminating our water sources. This essay explores the fascinating world of hydrogels and their potential to revolutionize ink waste management. We will delve into the science behind their remarkable properties. We will also examine how they interact with ink waste at a molecular level. Water flux refers to the rate at which water flows through a membrane. In the context of hydrogel filtration, it determines how quickly contaminated water can be purified. Ink concentration plays a crucial role in influencing water flux. As the concentration of ink in water increases, the water flux through the hydrogel membrane decreases. This is because the ink particles occupy space within the hydrogel matrix. They hinder the movement of water molecules. Imagine trying to walk through a crowded room. The more people present, the harder it becomes to navigate. This inverse relationship between ink concentration and water flux has important implications for designing efficient hydrogel-based filtration systems. Understanding this relationship helps optimize flow rates and ensure optimal filtration efficiency. Electrostatic interactions are crucial for the effective capture of ink waste by hydrogels. These interactions arise from the electrical charges present on the surface of both the hydrogel and the ink particles. Hydrogels can be designed to possess a positive or negative charge. This is done by incorporating specific chemical groups into their structure. Ink particles, on the other hand, often carry a negative charge. When these oppositely charged materials come into contact, they attract each other. This is like how opposite poles of a magnet attract. This electrostatic attraction ensures that the ink particles bind to the hydrogel. Thus, they are removed from the wastewater stream. The strength of this interaction depends on factors such as the magnitude of the charges and the distance between the hydrogel and ink particles. One of the most remarkable properties of hydrogels is their exceptional water retention capacity. They can hold a significant amount of water within their three-dimensional network structure. Imagine a sponge soaking up water. That's similar to how hydrogels work. This water retention capacity is attributed to the presence of hydrophilic or water-loving groups within the hydrogel's molecular structure. These hydrophilic groups, such as hydroxyl groups, form hydrogen bonds with water molecules. This creates a strong attraction between the hydrogel and water. The ability of hydrogels to hold on to water is crucial for their application in ink waste management. It ensures that the ink-laden wastewater remains in contact with the hydrogel for a longer duration. This maximizes the efficiency of the filtration process. Section 5. The role of hydrogen. Bonding and acidity in water retention. Hydrogen bonding plays a critical role in the water retention capacity of hydrogels. Hydrogen bonds are a type of weak chemical bond that forms when a hydrogen atom is shared between two electronegative atoms, such as oxygen. In hydrogels, hydrogen bonds form between the hydrophilic groups of the hydrogel and the oxygen atoms of water molecules. The acidity of the solution, measured by its pH, can also influence water retention. Changes in pH can affect the ionization state of the hydrogel's functional groups. This in turn impacts the strength of the hydrogen bonds. For example, at low pH values, the increased concentration of hydrogen ions, or H+, can compete with water molecules for hydrogen bonding sites on the hydrogel. Understanding the interplay between hydrogen bonding and pH is vital for optimizing the water retention properties of hydrogels. This ensures they can effectively remove ink from wastewater under various environmental conditions. Section 6. FTIR spectroscopy. Unraveling the chemical structure of hydrogels. To fully comprehend how hydrogels interact with ink waste, it's essential to analyze their chemical structure. Fourier transform infrared spectroscopy, or FTIR, is a powerful analytical technique used to identify the functional groups present in a material. It works by shining infrared light through the sample and measuring the wavelengths of light that are absorbed. FTIR analysis of hydrogels provides valuable information about the types of chemical bonds present in their structure. For example, the presence of a broad peak around 3,300 centimeters to the -1 in the FTIR spectrum indicates the stretching vibration of OH bonds, confirming the presence of hydroxyl groups. By analyzing the FTIR spectra of hydrogels before and after ink absorption, researchers can gain insights into the chemical interactions occurring between the hydrogel and the ink molecules. This information is crucial for understanding the mechanism of ink removal and for designing more effective hydrogel-based filtration systems. Section 7. SEM analysis. Visualizing the surface morphology of hydrogels. Scanning electron microscopy, or SEM, is a powerful imaging technique that provides high-resolution images of a material's surface. In the context of hydrogel research, SEM is used to visualize the surface morphology of hydrogels and to observe any changes that occur upon ink absorption. SEM images reveal the porous structure of hydrogels, highlighting the interconnected network of pores that allow for water and ink molecules to penetrate the material. By comparing SEM images of hydrogels before and after ink absorption, researchers can observe how the ink particles are trapped and distributed within the hydrogel matrix. Furthermore, SEM analysis can reveal any changes in surface morphology that occur under different pH conditions. This information is valuable for understanding how pH affects the hydrogel's structure and its ability to capture ink particles. Section 8. Practical applications, hydrogel filtration in industrial settings. The unique properties of hydrogels make them ideal candidates for a wide range of practical applications, particularly in industrial settings where ink waste management is a significant concern. Hydrogel-based filtration systems offer a sustainable and cost-effective solution for removing ink contaminants from wastewater. One promising application is in textile factories, where large volumes of water are used for dyeing processes, resulting in significant ink-laden wastewater. Hydrogel filters can be integrated into the wastewater treatment process to effectively remove ink and other pollutants, allowing for water reuse and reducing the environmental impact. Another potential application is in printing and packaging industries where ink is a primary component. Hydrogel-based systems can be implemented to capture and treat ink waste, minimizing the discharge of harmful pollutants into the environment. Section 9. Conclusion. A sustainable future for ink waste management. As we strive for a more sustainable future, finding innovative solutions to address environmental challenges is paramount. Hydrogel technology offers a promising avenue for revolutionizing ink waste management. Their exceptional water retention capacities, tunable surface properties, and ability to effectively capture ink particles make them ideal candidates for developing efficient and eco-friendly filtration systems. Further research and development in hydrogel technology hold immense potential for creating a circular economy in ink-dependent industries. By investing in these innovations, we can pave the way for a cleaner and more sustainable future. Hey everyone, welcome back to the channel. At the end of this episode, we're diving into something really cool: superabsorbent hydrogels and their role in revolutionizing waste management. First off, big shout out to the brilliant minds behind this research. Led by Dr. Mai Mostafa Mohamed from the Polymer Chemistry Department at the National Center for Radiation Research and Technology in Cairo, Egypt, this team is doing some groundbreaking work. They've teamed up with experts like Professor Dr. Saber Ibrahim from the National Research Center in Giza and Professor Dr. Salah Lotfy, also from the NCRRT. Their study, gamma irradiation synthesis and characterization of polyene, vinyl 2-pyrrolidone, acrylic acid, superabsorbent hydrogels for treatment of ink waste, was published just a few days ago. So, what's this all about? These researchers are investigating superabsorbent hydrogels. Think of them as super sponges that can soak up water but leave behind ink components. They're made using gamma irradiation, which might sound like something out of a sci-fi movie, but it's actually a very controlled and precise method. Water retention is a big deal here. The team found that hydrogels made at lower irradiation doses, like 5 and 10 kGy, held the most water. That's critical when you're trying to clean up ink waste, especially in different environments like air and acidic conditions. Using FTIR spectroscopy, they identified the key functional groups that make these hydrogels so effective. We're talking about carboxyl groups, aliphatic hydrocarbons, and ester groups, all playing a part in absorbing water and repelling ink. This research is a huge step forward for sustainable waste management, especially in the printing industry. Imagine a world where we can efficiently separate ink pollutants from water using these innovative materials. What do you think about this approach? Drop your thoughts in the comments below. And don't forget to like, share, and subscribe for more fascinating science content. See you in the next video.